Hey everyone, thanks for joining my talk today. My name is Markus. I'm a solutions architect at Amazon Web Services, AWS. And as a solution architect at AWS, my job is to help customers solve their business challenges using AWS technology. And for some of my customers, the solution for the challenges on Earth actually lies in space. And that's why I work quite a lot with AWS GroundStation to help my customers succeed in their missions to use space data, satellite data for their business challenges. What I want to do today is explain a bit how such an Earth observation pipeline that I'm going to show works in general, but then really be hands-on and show an actual satellite downlink of a NASA weather satellite and talk about all the components that are required to get data from the satellite to Earth in a format that is useful to humans. So to start off, I'd like to speak about what a ground station actually is. The Wikipedia definition would be it's a terrestrial, that's the wrong button, here we go, terrestrial radio station designed for extraplanetary telecommunication with a spacecraft. That is right. But there's a simpler way to put it, and it acts as a link between a satellite and the Earth. It receives satellites from signals from the satellite and sends commands back to space, controlling the satellite and retrieving data. It works in conjunction with other ground-based facilities, a command and control center, data centers, and many, many more. The ground segment is made up by antennas, the command and control units, but also the launch facilities, and the space segment is made up by the spacecraft, mostly satellites. What we see on the right, on the left, that is a ground station, and that is probably one of the OGs of ground stations. That is the Parkes Observatory in Australia. That's the one that was used to broadcast or to transmit the data from the Apollo 11 mission from the moon. It's still in active use, and the general principle of such a ground station has not changed in the past 60, 70 years. Modern ground stations have a few more bells and whistles attached, but the principle remains the same. When you design satellite systems, there are a number of challenges, and they essentially all come down to one fundamental truth, is that the data value that you get from the data you downlink is closely connected to the latency it takes for you to get the data. And that is a challenge because these are hugely complex systems with many different parts, and the complexity contributes to the latency. So you have the ground station, so there's the satellite, you have the antenna dishes, you need to process the data, put it somewhere. That's what we call acquisition. Acquisition adds latency to the process. Then there's the processing. This is very compute heavy. You have the specialized software that just takes the readouts from the instruments on the satellite, and you need to process the data. You have quite big data volumes when you get a satellite downlink that you need to process and you need to store. Again, these are quite expensive operations, both in terms of time, but also in terms of upfront investment. You need to build out the infrastructure for this. So transport and processing also adds to the latency of that it takes for you to get value out of your data. And then lastly, you need to distribute the data. At the end of the day, a human, in most cases, needs to look at the data and just take conclusions and act on the data. That's what you want, both in Earth observation for, weather forecasting, or if it's intelligence data you're looking at. At the end of the day, it's almost always a human that needs to act on the data. And AWS GroundStation is a service by AWS, by Amazon Web Services. And it is a fully managed service that lets you control the satellite communication and in general scale your operations without having to make this huge upfront investments. You can use GroundStation to communicate with objects in the lower Earth orbit or in medium Earth orbits. So up until here, most satellites are closer to in this area. There are certain frequency bands when it comes to satellite communication, and ground station supports communication in the S and in the X band. The other bands are reserved for military and other use cases. What it does is essentially it removes the complexity of building your own ground station infrastructure. And it does so by offering the low latency global fiber network of AWS, so you get data quickly from the point where it arrives at Earth into your data center. You get fully managed antennas, so you just rent them like you rent servers on AWS, you pay as you go. You have direct access to the entire cloud resources at AWS. There are no upfront costs, you pay per minute, so if the downlink is 10 minutes, you pay for 10 minutes. There's no licensing requirements. Licensing can be quite complex, especially when it comes to software-defined radios and all the aspects that you require for space communication. You can have programmatic scheduling via the API. Those of you that have used AWS before know there's a strong tooling around our APIs, the CLI, the SDKs. You can use all those to schedule contacts with a satellite, which makes it great for automating things. We're going to see that later. And lastly, you get global coverage. Because if you build your own ground infrastructure, not only do you need it in one place, but you need it globally, because the satellite, you ideally want to scan the entire globe, and then you need ground stations in different places on Earth, and that's exactly what we built. So what you see here is, you see the locations of our antennas. Currently there are 10, nicely distributed, both in terms of latitude and longitude. So that you have many windows for contact with satellites that orbit the Earth. You also have console locations. So those of you familiar with AWS, those console locations correspond to regions. A region in AWS is a place on Earth, a geographical location where we have clusters of data centers where you can run your workloads, where you can harness the full power of AWS, so compute power, storage, and so on. And the way this works is the satellite orbits the Earth, and then there's a window to downlink data from the satellite. In this case, that would be in Cape Town. But the next window might be in Hawaii or in Seoul or wherever. You don't want to deploy your workloads across the globe. You want to have it in one place, for instance, in your data center in Frankfurt. That's where you want to have your workload, your EC2 instances, where you do the heavy computing of the data. And what is then happening is the data is downlinked at one of the antenna locations and sent to the compute infrastructure that you have in place somewhere in these console locations via the low latency fiber network that AWS owns. So that gives you a low latency. And this is not only possible for one location, but for all antenna locations. So get all the data in one place. So you need global coverage. You just schedule contacts for every antenna location and get the data all in one place. This is helpful for a large number of common satellite data processing use cases. So there are many, but those are the most common ones in the commercial sector. There's weather forecasting and agriculture, so where you want to monitor crop health and water levels, for instance, to predict the yield of the harvest. That's an interesting use case. Global shipping and anti-piracy, where you track the transponders of the vessels, also for illegal fishing, for instance, and there you correlate this to the data you have from the ground station to identify vessels that are somewhere where they are not supposed to be. Retail forecasting is an interesting one. If you have a high enough resolution on the satellite, you can identify individual cars on a parking spot, for instance, and research has shown that this is a strong indicator of to forecast the revenue on a given day. And lastly, that's the one we are going to do today, Earth observation. So what you want to have is you want to have a high-level overview over different parameters of the Earth, like water, clouds, all the things that help to predict climate and weather. And what we are going to do is we're going to use a weather satellite, NOAA 20, which has been launched in 2017 by the National Oceanic and Atmospheric Administration. into orbit. It has the NORAD ID 43013. NORAD is the North American aerospace. I don't know what the acronym stands for exactly. It essentially, every object that orbits Earth has a NORAD ID to identify it. So satellites, the ISS has a NORAD ID. It is part of the Joint Polar Satellite System, and it's also called JPSS-1. That was the sort of working name while it was built. Now it's officially called NOAA 20. So if you read JPSS-1, it refers to the same satellite, just a different name. What it does is it provides the majority of data that informs the numerical forecasting of weather for the US. And it also delivers critical observations and data points for severe weather events like blizzards, thunderstorms, hurricanes, and so on. And to do this, it carries 5 instruments that track different things across Earth. And one of the instrument is it's a bit hard to read for you, it's the Visible Infrared Imaging Radiometer suit. This is essentially a radiometer that scans the Earth continuously in the infrared and visible light spectrum. And it just tracks the data and then sends it back to Earth. And that's the data we're going to use today. So there are others that track ozone and other parameters, but we are going to look at the readout of the radiometer. And then it continuously broadcasts the data to Earth. It has been launched, as I said, in 2017 in November from Vandenberg Air Force Base in, I believe, California. That is a picture of the actual launch. I think this is quite a cool picture. I wanted to include it. And it orbits the Earth in around 830 kilometers in a sun-synchronous orbit. So sun-synchronous orbit means that the angle between the orbit and the sun will always be the same. That is important if you read visual data from the radiometer, because otherwise the different angle of the sun would distort the data and you would not get predictable or reliable results. It orbits the Earth once every 141 minutes. So, and that gives it a full global coverage twice a day. It is part of a constellation of currently 3 satellites of the same family, I would call it. 3 of them have been launched. The most recent one, JPSS-2, called NOAA 21, accordingly, has been launched only 6 months ago or so. And the plan is to build up a constellation of 5 satellites until 2032. And what they're going to do is they're all going to be on the same orbit and will then circle the Earth and continue to scan the data. And that gives you a very low latency for any given point on Earth and a very high coverage for any given place on Earth. And I scheduled 2 passes. One is already done. So that was like probably an hour ago, 45 minutes ago, where the NOAA 20 satellite passed the US West Coast and sent data to one of our ground stations there. That data has now then been sent to AWS. And there's a second pass that we might have a chance to see, but there's not too much to see there, I need to warn you, which will be in about 20 minutes or so, 30 minutes, and that will be over Northern Europe. So this is where the satellite is right now. Let's see. Yeah. So you can see here, the satellite passed over North America. No, here, that's the one. That's the orbit that it passed. And now it comes down here. Now it's over the Antarctica. And now it works its way up until it passes over Northern Europe or Europe, Central Europe, Northern Europe here, the Scandinavia, and then goes back. And in that window, roughly, it's where we're going to downlink data. We also did downlink data in that part of the of the orbit, and that's the data we're going to process now. Before we dive into the actual components that make up the Earth observation pipeline, I want to talk about two more things. One is the data processing levels. So there's a lot that needs to happen for the data that is recorded by the satellite, for that to become useful to humans. So a lot of steps need to be taken, a lot of processing needs to be done until you have data that can be used. And I'm going to use the terminology in the course of the talk. So just keep in mind roughly what they mean. So it starts with the raw data. This is raw telemetry data that is sent from the satellite to Earth. All transmission data, science data, engineering data is embedded, so it's essentially just, it's binary, it's zeros and ones. There's nothing that you can do with that data that is useful at this stage. What you then need to first do is process this to level 0 data. This is the full resolution data, but still unprocessed. There are some communication artifacts removed, like synchronization headers and other things that are just required to make the transmission work. Examples could be raw instrument voltage. So instrument has a readout and it doesn't really convert this to like a unit that humans would understand. It's just like voltage, and that's the data that the satellite reports, or measurement counts, for instance. That's the kind of data you get at this stage. And once we have this level 0 data, then we go on, then we process this to level 1 data. That is still data at the full resolution, but this is processed, and this is then converted to metrics that are a bit more intuitively understandable to humans. So brightness would be an example. Surface temperature, that's something that is understandable, that you can at least understand the concept of, and correlate this to other values like time and geolocation. So if you have the time and the geolocation and you have the surface temperature, that's data you can understand. This is typically stored in HDF files, so that's the hierarchical data format, which is more or less the standard for these kind of workloads. It allows you to pack a lot of data into a very dense format and compress it across multiple dimensions. For instance, it's hard to read. It's temperature, pressure, elevation, land cover, but also on the latitude, longitude, and time scale. This is, for instance, the data you use if you would do weather forecasting, if you would have some numerical computations that want to predict weather based on the data. And lastly, the data we're going to get is L2, which is the same resolution and location as the L1 source data, but you combine different metrics of the source data so that the data becomes even more meaningful. An example would be you look at the cloud top temperature, which is one of the metrics you get, and you look at the land surface temperature that you get, and then you correlate this and you can track wildfires, for instance, or sea ice concentration. Or you can just get a true color image. So this is like how the Earth looks like from the view of the satellite, essentially. This is the same image that's North America, there's Cuba, that's the East Coast. That's the land surface temperature, I believe, in August last year. And that is data that is now really, that's easy to understand. If I show you this data and tell you this is North America, it's quite clear what it does. And that's what you can look at and work with. So the second thing I want to talk about are the AWS services used. Just for those that are not that familiar with AWS, there are a few more services involved to make the architecture that I'm about to show work. First is AWS Lambda. AWS Lambda allows you to run code in response to events without having to run servers. So this is typically used, in this use case, we use this for automation. So some event happens and I want to react. I want to start an EC2 instance, a virtual machine. via an API call, or I want to convert some data in a different format by stripping away some bits or something like that. Then we have Amazon EC2. That is compute capacity. Those are essentially virtual machines. That's where the heavy lifting is happening. That's where the software runs that converts the data throughout all those stages, from raw to L0 to L1 to L2. Then we have the simple storage service S3. That's just a scalable and highly available cloud-based storage. We put all data there, so when the satellite downlinks the data, it ends up in S3, and then it's just taken from there, synced to the local to the machines locally just on the file system, on the local file system, processed and synced back, and then the data, once it has been processed, ends up in S3 again. We have Event Bridge. This is an event bus where you can retrieve events from AWS. For instance, one event would be that the parse has finished. We're going to see that in a second. And then you can react on this. So you build this event-driven automation around this to have really this pipeline that you want, where you don't have any human intervention. And lastly, the simple notification service. This is just a messaging service that allows you to send notification to humans, but also to machines. Humans in the form of emails, machines in the form of some push notifications to some endpoint, for instance. All right, that's the architecture. That's simplified quite a bit, so there's a lot happening that is not shown, especially here in that area on the EC2. But in general, this is a one-time setup, and then it's an automated process. The one-time setup takes between 2 and 3 hours, and this is mostly due to licensing requirements by NASA for the software we're going to use. That is a manual process that cannot be automated. Once it's set up, the process is automated, and it's split into 4 main parts. So what we have is the downlink part here, where we have the ground station. It just takes the data. Then we extract data, where we create the L0 data products. Then the process, where we create the L1 and L2 products. And then the analysis phase, where we upload the data somewhere, apply machine learning, bring it in a different format so that humans can work with it. The process is started every time you schedule a contact. And then the time it takes until you get results is about 10 minutes for the L0 products and 30 minutes to 90 minutes, depending on the configuration, the size of your virtual machines, and so on, until you get the L2 products. And along the way, you will retrieve, or the controller, in this case me, will retrieve notifications about the state of the pipeline. So when we look into the downlink phase, what you need to do is configure a mission profile. And that just tells GroundStation how the contact is to be executed, like what to do to make the contact work. It configures the software-defined radio, if you want to use a managed software-defined radio by AWS. But it also configures the physical antenna. It tells the physical antenna where to point, like the satellite is there, point the antenna this way, and then just follow the satellite. That's what you tell it. It's quite complicated. Those are the sample configurations, or those are configurations that I'm using for JPSS1. That's demodulation config, that's the decode config, and you just define what's the algorithm. That's a phase shifting algorithm. You define some frequencies, and that's just required for it to work. When there's a contact and GroundStation retrieves the data, it demodulates and decodes the data and then puts it somewhere. And there are 2 ways to handle this. There's the asynchronous way, where you put the data to S3 and GroundStation takes care of decoding and demodulating. That's when you need these configurations. There's another way, which you would use, for instance, if you have some proprietary formats, some encryption applied, where you define your own software-defined radio on an EC2 instance, and then GroundStation just really takes the data in a digital intermediate frequency format. That's just like an industry standard to work with those sort of use cases. And sends it as UDP packets to your instance. And then you have some data defender running that takes care of all the other things that we can manage for you. What we're going to do today is this. This is the simpler use case, and for a broadcast satellite that just makes the data publicly available, this is perfectly fine. What we're going to see is that the raw packet capture data is written to S3. It's just stored away. And GroundStation will then emit the GroundStation downlink complete event to the event bus that will then trigger the workflow. So if we have a look at that's the AWS console. I guess some of you might have already seen this. That is just the UI, the web UI to interact with AWS services. So this is how you reserve a contact. We need to get the satellite catalog number, so the NORAD ID that is on the slide, and then the correct mission profile. That's the mission profile, so JPSS to S3. And then if we adjust the time, go back a bit, maybe like this. Yeah, there are two contacts. That's the one over Oregon. Can you see it? Should I increase the font size? I'll increase the font size. All right. So that's the one that was done earlier. That is completed. There's another one that is scheduled. So this is UTC time, so +1, which means in, I don't know, 50 minutes or so. You can do the same thing using the CLI, or in general, any form of automation, the AWS SDK, the AWS CLI. Okay, so 1 second. Okay, I need to copy the command. So this achieves the same thing. So this is the CLI, which would be the typical way to do this if you want to automate this. Okay. All right. Yeah, it's a live demo. That's how it's supposed to be, I guess. Maybe? No. Well, all right. I think you're going to believe me. What this would output is a table that lists the contact, and that's how you would use it to automate things. All right. What we also see is that the raw data has been sent to the S3 bucket. So, oh, come on. Here. So that is the S3 bucket, the data, JPSS1, 2023, May, and today is the 10th. So, and that is the raw data. That is the packet capture files. There have already been created some binary files. That's going to happen in the later step. And what you should also see is a notification has been sent out. All right. So if we look at this, there's now an EC2 instance running that is processing the data. So after we got the data from the satellite as the packet capture in S3, the GroundStation downlink complete event triggers a Lambda function, and that Lambda function just executes some Python codes that extracts the actual payload and puts it into a single binary file, bin file that is stored in S3 again. It then uses the AWS SDK to programmatically start the EC2 instance that is responsible to process the data from raw to L0. That is happening on the extraction EC2 instance. On the EC2 instance, there's a software called Real-Time Software Telemetry Processing System. So that's quite a mouthful, RTSTPS. That is software written by NASA that just knows how to extract this raw data and put it into L0 data for a large number of satellites. It takes the raw data, it processes into L0 data products, and then puts those data products back into S3. After it processed the data, the instance shuts itself down and notifies the downstream consumers of the pipeline that it is finished. And then we head to the next phase, which is the data processing. That's where really the heavy lifting is happening. And the data processing instance is started by a Lambda function. That Lambda function, again, is invoked as a reaction to the event that we sent out, that also notified me via email. And on this EC2 instance runs the International Planetary Observation Processing Packet, again, not a mouthful, which is part of the Direct Readout Laboratory by NASA that allows anyone to work with that satellite data and to process that satellite data. That can be you, but typically those are research institutions that are not associated with NASA. That's the target audience of IPOP. It also processes sensor data from a wide range of research satellites, including the JPSS missions, but also Aqua, which is an older research satellite that was used to research the water cycles on Earth. When the instance starts up, there's a script running that checks for new L0 data that has been created in the previous step, and then it syncs it to a local folder, starts the processing, and syncs the data back to S3. It's a Java client that runs on CentOS and processes the L0 files into higher level products by combining the instrument readouts. And the way this looks like is, so these are the two instances. That's the RTSTPS that has been launched but already finished. It should have created the L0 data. Let's see. Let's reload this. Yeah, that's our downlink, so it's 1.4 GB. That has been created by the Lambda function. This is still the raw data. It's just taking the packet capture, stripping away all the unnecessary parts, extracting the payload, and putting that into one binary file with 1.4 GB. After that, the RTSTPS instance processed that data into the level 0 data that reflects the actual instrument readouts. So these are the PDS files. Okay, somehow the font size is not increasing. Can you read this? Okay. So if we reload this, and yeah, here we go. So now we have some new files like PDS file, H5 files, where the L0 data, the actual readout is stored. So those are large files that contain the voltage and all the data I just mentioned. We can have a look at the logs to see what happened at the RTSTPS, because there's nothing that you can see visually, but we can look at the logs and data capture log. I think that's the one. Second. Here. So those are logs written by RTSTPS. It's a lot of gibberish, but here it becomes more interesting because what we see here, those are the different instruments that the satellite is carrying. So that's the radiometer, that is ozone tracking and a few others. And then you see how the data is processed. I'm just scrolling over it. And at the very end, what you can see here, those are different metrics, more or less, that are read out by RTPS from the data that the satellite sent to Earth, and those are then put into those files, and then those are used to process it further. So this was the extraction step. Now that's the processing step, which seems to have failed. Fantastic. But it's not a problem. There's not much to see anyways. So something happened in the IPOP phase so that the data did not get processed, but we wouldn't be able to see this anyways because it would take roughly an hour for this to complete. But I have data from previous missions to show. What I can show nonetheless is the iPod visual interface, the user interface. So what I need to do is create a tunnel. Now that's the instance, and go to here. Is this working? I think it should. All right. Okay. Just a typo. So now I'm on the processor instance that is running the NASA software. And if I go to the terminal and open the dashboard, yeah, this works. So this is the iPod dashboard. What you can see here are the tabs for the different types of satellites. So EOS, that's an older mission. That is the tab for the radiometer on JPSS-1, Aqua NOAA 20. And if this would have worked, you would have seen that these SPAs, they are called, they just create different data products. They should be running. They would create data and process the data into these higher level products, L1 and L2. Those would be the tab for the other instruments of the satellite that we're not going to use today. And yeah, then this would finish again after 30 to 90 minutes. This typically in this configuration takes closer to 90 minutes, just because it's a lot of processing going on, a lot of data products are going to create it. If you would be in a real world scenario only interested in one particular readout, in one particular data product, you could deactivate all the others, maybe have a greater EC2 instance, like a more powerful instance, and speed things up quite a bit. But 30 minutes is roughly the lower end of what you can achieve, at least what I managed to achieve. Yes, so when this has finished, there are a number of new data products created, which is again in this 3 bucket. Level 1 is not super interesting, at least not for us. This is mostly like these HDF files for scientific computing. That's not super exciting. Things become more exciting when we look at, let's put this away, at the L2 products, because in there we have TIFF files. That's an image format, and that is something that we can look at. And as you see, there's no data from the past today, but this is a previous past that I did in preparation for today's talk. And we can have a look at the data. So how do I do this? Let's go back. Now it's the analysis phase. So what you can now do is work with that data. You have the L1 and L2 products. Well, we don't have the L1 and L2 products for that pass, but in general, we have data. You would put the HDF files for scientific computing. For instance, now the data is in a region. You can now spin up thousands or tens of thousands of virtual machines and do the numerical weather forecasting. That can happen more or less in real time, not the forecasting, but spinning up the data, spinning up the infrastructure to do the forecasting. You can do this while you process the data in the same fashion that I automated the rest. And then right away start crunching the numbers and predict that it's going to rain in London. What you can also do is you can take the TIFF files that have latitude and longitude information embedded and put that into a 3D space, for instance, Google Earth. You can also have some interesting machine learning use cases. For instance, the one that the French government did. What they did is they took aerial images and trained a machine learning model to look for swimming pools. And in France, there's a tax on swimming pools, but it's apparently not everyone likes to pay the tax. So what they did is they analyzed this aerial photography and correlated that data with the records they had on registered swimming pools. And to no one's surprise, there was a large gap where then some taxation and some fines were applied. There are some machine learning applications that are built into the processing that are already in there. For instance, for fire detection. So what iPop does is it creates a data product which is called Fire True Color, which takes the true color image of the Earth, but also takes other readouts like land surface temperature and a few other readouts to predict where there are wildfires. And that's what I want to show, among others. So let's see, that is Google Earth. And what I have here is I imported a few of the GeoTIFF files from previous passes already. So what we can do is let's look at the west coast of the USA. Oops. Oh boy, what am I doing to this globe? Now it's roughly okay. So this is an image taken, I believe, last year in the summer. That is a true color image of the west coast of America. That's an overlay, so if I deactivate it, it looks pretty much the same. And what you can see here, that is machine learning. Yeah, I think you can call it machine learning. That is already applied to the image by iPop. So it correlates different data points to determine, okay, there is likely a wildfire in the Warm Springs Reservation or down here near Lakeview. And this is quite useful data because you look at it, then you have an immediate overview over areas where there's a risk for wildfire, where there are already wildfires going on from a very high level view. You can also look at different data. You can look at the land surface temperature, for instance. That is, again, data from last year, I believe. This time for the west coast. No, that's the east coast. For the east coast. And this is the land surface temperature. There are a few areas where it's black. That's where clouds are. Clouds are the mortal enemy of satellites. But you can see it's quite hot in the in the Midwest. Here, Nebraska, Colorado, Kansas. It's a bit cooler to the north, which is expected. And then it gets hotter when you go down south. And yeah, this is quite interesting to put the data on such a globe. Another use case that I want to demo is actually what France did with swimming pools. So what I did for a different talk, for a different demo, is I trained a machine learning model to recognize swimming pools. So what I did is I just took some aerial images, split it up into tiles, and then created a sample data set of 79 labeled images where I marked the location of swimming pools, and then I retrained on existing models that's provided by Amazon Recognition, one of our machine learning services that we offer. And what I can then do is take some unlabeled data that I have here, For instance, this one. 1 second. If I open it, that should work. Yeah. So that is an image from it's an aerial image with swimming pools in it that has not been labeled. And what I can now do is go here. Let's see if that works. Okay. Again, using the CLI, the AWS CLI. Oops, that's the wrong terminal. Yep, that worked, fortunately. So what we can now get is that with a high confidence, we found 4 swimming pools. No, 3. All right, it's not a perfect model. If we increase the number of training data, images in the training data, it should be better. But we identified that there are swimming pools in that image. And we can then take the information about the width of the image and correlate that to latitude, longitude, and then map it to actual information where on Earth this is. And yeah, lastly, you can look at all the downlinks I did. That's part of the automation. If you go to this page, it is linked here. This is just a redirect, or scan the QR code. Then you will come to a page that looks like this. I'm a great web designer, I know. But the data is there. So this is the first pass, which is in August. This is COT cloud. I think that's the cloud top temperature, something like that. I'm not entirely sure. So that's a different data set. And you can just scroll through it. There are some cool images of Earth, land surface temperatures, and so on. So yeah, go ahead. See for yourself, and thank you. Questions?
Yeah, hey. I don't know if it's working or not. Okay. As I understand, there are satellites that just broadcast the data, and basically anyone can do what you do.
Mm-hmm.
What you did. Is there any reason to do this ourselves? Isn't NASA or some owner of those satellites getting all the data anyway, like for 24/7? Then they could provide us with already preprocessed data instead of us getting it like all the way by ourselves.
Mm-hmm. So you're spot on. Data, the data is provided by NASA, but there's a delay. Like they take the data, and I believe they make the HDF files available to the public. So for that particular satellite, you could use that data as well if you're willing to accept a larger delay. If you have a use case that requires you to get access to different data, to have a different form of processing, then you would be using this process. This is an example. There are other providers that have their own satellites, and they want to have very specific use cases, and the data is published nowhere else because it's their satellite data. And then you're back to a process like I just described.
I was just hello. Oh,
Yep,
it's working.
we can hear.
I was just wondering, is there also CloudFormation support for configuring all of this?
It is. The entire project is automated via CloudFormation and the CDK. So there are a few manual parts, again, related to licensing requirements of the software, where you have to do manual steps. But overall, the pipelines are the Lambda functions, event bus, the EC2 instances, the startup scripts, that is automated. There's a GitHub project where a colleague of mine published this CloudFormation, the CloudFront templates. I myself did some work with the CDK to automate this even further, but overall this can be automated really well.
Just following up to the first question, do you have any entry point or any link or anything for that kind of NASA data?
Yeah, I have. I need to look it up. It's on the website of the Direct Readout Laboratory. So if you Google DRL NASA and then maybe JPSS1 products, that should point you in the right direction.
Okay, thank you.
Any more questions?
So for the demo you had, roughly how much would that cost?
I was expecting that question. So that is the pricing. It depends on the band that you're using and then per minute. So the pass I had was, I believe, 10 minutes. We were using the narrow band. No, we're using the wide band. So that pass would be around $220 when scheduled on demand. For reserve capacity, like with EC2 instance, things become cheaper. And then there's the cost for the data processing, but that is not really related to the satellite and for the EC2 instances. So only the pass would be in the ballpark of $200. Any other questions? All right. Okay, there's another one.
What's the highest resolution that you can get from the satellites?
It depends on the instrument. I don't know. I think it's a few kilometers. I think for the radiometer, it's 10-ish kilometers per pixel. So, but this is just this satellite. There are others that give you a much better resolution. Or you're talking about the output of the image, like the resolution in terms of width and height. Okay. And it really depends on the use case. If you want to track swimming pools, you need to have a higher resolution. But if you want just get weather data, ideally you have you zoom out quite a bit because you want to capture a large area. Any more questions? All right, then thanks a lot for coming to my session and have a great day.